In this lesson, we will be looking at graphing linear inequalities. So let's first recall what is a linear equation. So recall from the previous chapters, we had ax plus by equals c. So since this one has an equal sign, we consider that an equation. But this says linear inequalities. So we now have four types of linear inequalities. They are ax plus by less than c, ax plus by less than or equal to c. We also have ax plus by greater than c, and finally ax plus by greater than or equal to c. Now let's look at the solutions to an inequality, a linear inequality. So a solution to a linear inequality is an ordered pair, x, y, that makes the inequality true. So whenever we take the x and the y and substitute it back into one of the original linear inequalities, that is a solution to the linear inequality. The next thing we need to talk about is a boundary line. Now, a boundary line is simply a line that separates the coordinate plane into two regions called half planes. And that leads us straight to here, what is a half plane? So a half plane is going to be these pictures over here. You can see here we have an open line. It is dotted through here, and then it is shaded on the top. So if you extend this line up this way and down this way, it is cutting the coordinate plane into two regions. So when we consider this to be open, this is open because it does not include the line. It does not include the line. Now over here it says closed, and you can see that the closed line is completely solid. So it's completely solid, and that's going to be considered a closed half plane. This does include the line. Now, what makes opened and closed? Well, for open, it is going to be greater than or less than because you are missing the equal to, so this is going to be dashed. And closed is going to be greater than or equal to or less than or equal to, and this is going to be solid. So now let's look and see how we actually graph a linear inequality. We currently have 3 steps to do this. So here we are going to, step 1, graph the equation like we already know how to do. And the best method to use here is going to be slope-intercept. Step 2 is to determine if the line is solid. Now remember, solid is going to be one with equal to, or dashed, and dashed is going to be one without an equal to. Now, step 3 is critical. This is what the inequality forces us to do. We then pick a point not on the line and test it in the original inequality. Now, we always shade the side that is true. And when we test a point, it is also ideal to pick one not on the line. So if 0, 0 is not on the line, we consider that the easy one to test. So let's go ahead and look at number 1 so you can recall what we are talking about. Now it's going to say to graph the linear inequality. So when we're dealing with an inequality, that is going to force us to shade. So our first one is y is greater than 4x minus 3. And I want you to know what this forces us to do. So this right here is going to force us to shade the graph. So it forces us to shade the graph. So we are going to go ahead and graph this just like normal. So step 1 says graph the equation. So I'm going to treat this equation just like slope-intercept form, y equals 4x minus 3. So I graph the negative 3, I count up 4 over 1, up 4 over 1, and I see if it's going to be solid. So step 2, I'm dealing with a greater than, so that is going to be dashed. So I come through here and I dash my line. Make sure you can tell that it is dashed. So step 1, graph the equation. Step 2, determine solid or dotted. Step 3, we are going to test a point not on the line. Now 0 is right there, 0, 0. You can see that is not on the line. So if possible, try to always test 0, 0. Now, we put 0, 0 back up here into the x and y. So we have 0 is greater than 4 times 0 minus 3. 0 is greater than negative 3. Ask yourself, is that true or false? Well, that of course is a true statement. We always shade on the true side. So now if I shade my graph, you can do this with your pencil, you are going to shade on the true side. Now earlier we talked about solutions to the inequality. Now I need you to realize that every dot you see, everything in this shaded region, not on the line, those are solutions to the inequality. So for number 2, I would like for you to pause the video and do number 2 by yourself. The problem is y is less than or equal to negative x plus 3. Pause the video and do the exact same thing I just modeled in number 1. Okay, I have graphed the equation here. I've graphed it here. I figured out that it was solid, and I have tested a point 0, 0 because it was not on the line. Now, when I have tested it, I have got a true statement. I always shade on the true side because that means that's where all of the solutions are. So I'm going to shade on the true side. Now, that is the 3 steps that we always follow when we are graphing linear inequalities. Number 1 and number 2 both have in common slope-intercept form. Now let's move to number 3 and number 4. Number 3 is not going to be in slope-intercept form. It is going to be y minus, or x minus 2y greater than 0. So the first thing that we need to do is we need to put this in slope-intercept form. So we have negative 2y greater than, I'm going to move the x over here, so negative x plus 0. Now I am going to divide by negative 2. The rule is whenever I divide by a negative, I must switch the inequality around, and I have 1/2 x plus 0. So I'm going to plot this at 0. I'm going to do up 1 over 2 for my slope. I'm going to go backwards. That is my first step. So step 1, graph that equation. Step 2, determine that this is dotted because I am not dealing with an equal sign. So I'm going to dot this line. And now we encounter a problem. This line is in fact going through 0, 0. So when I test the point for this next problem here, I am not going to use 0, 0. Now in fact I can use any point not on the line. But the next easiest one to test, in my opinion, will be this 1, 1 right here. So I'm going to test 1, 1 and see if it's true or false. I'm going to test this back up into the original equation. So I have 1 minus 2 times 1 greater than 0. So 1 minus 2 greater than 0, negative 1 is greater than 0. Now, of course, we all know that that is false. Negative 1 is not bigger than 0. So now I have a false. Now, if that side is false, that means this side is true. So I am going to always shade on the true side. Now, I want you to notice a pattern now. I have tested all 3 of these. And in all 3 of these, we have tested a point. Well, now I'm going to show you somewhat of a shortcut. Now, if you notice, this equation was in slope-intercept form. This equation is in slope-intercept form, and we put this equation in slope-intercept form. So for these, you can now just look at it and notice something. Greater than was on top of the line. Less than was on the bottom of the line. Less than was on the bottom of the line. So that will always happen if it is in fact in slope-intercept form. So now as we do number 4, you may notice something a little bit different. So you can just look at it now. So now again, I would like for you to do this problem. 2x minus y less than or equal to 3. I don't care how you do it, but remember you must put it in slope-intercept form and be careful with the negative. So please pause the video and try number 4. Okay, you can see here that I have placed the equation in slope-intercept form and I have graphed the equation. Now, I have not tested a point because I am going to use the strategy of, this is in slope-intercept form, and this says greater than. So I know that here is my line, here is the half plane, and I know that greater than will be on top of the line. And I know that simply because this is greater than, so everything will be on top of this. Now, if you don't like doing it that way, you can always, of course, test 0, 0. You could put it in up here. 0 is less than or equal to 3. That is true. That is true. We have shaded on the correct side.